Okay, so let me give a brief overview of regarding how we could possibly constrain nuclear equations of state, mostly through gravitational wave observation. And before doing that, I would like to give you a brief background of why it is considered very important and what other astronomical observation can provide, and their pros and cons, and why possibly gravitational wave can help a lot to shed a lot of light in this area. So first, let me begin with a disclaimer. Constraining neutron star equation of state is a quite rich and vast area of active research, and it's perhaps not possible to cover everything. And to do justice of each subtopic in this short duration presentation, I picked a very few handful topics which are mostly relevant in this context, and it's also maybe limited by my knowledge and also my personal bias. And any omission of any significant aspect is highly regretted from my side, and I will be love to hear from you. So content of the talk. So I will briefly describe importance of neutron star equation of state, how it can be seen as an aspect of fundamental physics, and present constraint coming mostly from massive neutron star observed through radio observation, and the requirement of radius estimation, the pros and cons of X-ray observation in this context, and prospects of what gravitational wave can do to measure the primarily the tidal reformability, but also a little bit on the post-merger phase I will touch upon, which can potentially also constrain the neutron star equation of state. And prospects of constraining equation of state, I already mentioned from NR simulation, which is essentially the post-merger phase. This is a very broad brush picture, a brief picture of neutron star. Its typical mass is 1 to 2 solar mass. Upper limit we don't know, but recent observations show that it's at least 2 solar mass. Stable neutron star is really possible to form in our nature. Radius is 15 kilometers, which is essentially, if you look at all the realistic equation of state, possibly 9 to 14 is more real practical bound, but if you relax slightly certain condition of nuclear physics front, you get roughly 8 to 15 kilometers. That's fairly robust bound. Density definitely in the core it's very high, and in the surface it's quite small. But most of the matter, say 90% of the mass, is confined in a region where the density is around 10 to the 11 to 10 to the few times 10 to the 15 gram per centimeter cube. And the exact density, of course, depends again on the equation of state. It has a huge magnetic field, possibly the largest magnetic field you can see anywhere in the universe on the neutron star. And its surface magnetic field goes somewhere around 10 to the 7 for low mass X-ray binaries to a really massive neutron star, like really highly magnetic neutron star like magnetar, where 10 to the 15 Gauss is the surface magnetic field. Now, composition in the interior of the neutron star is quite uncertain. And core of the neutron star, it consists of supranuclear, cold and dense degenerate matter, which is a very different form of matter than we see in our terrestrial laboratory. It's quite difficult to predict these type of matter properties, as I will try to very briefly elaborate from theoretical first principle like lattice gauge theory, where you require a density which has to be very small, and at that large density you cannot write the properties of matter. So this is a QCD-phase diagram, a schematic picture, and here various early universe and our terrestrial collider physics lie, where you have in x-axis this baryon chemical potential. That's also you can think of as as density, matter density, and in the y-axis you have temperature, and you can see that early universe explores very high temperature, very low density region. And the rich relativistic heavy ion collider experiment in BNL explores this part of the region of your QCD phase diagram, this strong interaction phase diagram, and neutron star matter, matter inside essentially the core of the neutron star below here, where temperature is really, really small. It's much smaller than the Fermi temperature, but density is really high. So this part is completely unexplored by any other fundamental physics aspects like experiments or cosmological observations. So this is a very unique part, and it cannot be produced in the laboratory. It cannot be derived from the first principle theory. So it's certainly a part of the fundamental physics aspect that neutron star uniquely provides. And it happens that nature provides us the laboratory in the core of the neutron star where we can probe this type of matter. So that naturally calls for astronomical observations to look for this type of matter in our universe and understand their properties in details. Now, here I plot a handful of neutron star equations of state, where in the left panel you can see density as a function of pressure starting from very low density, where our understanding is much better. This is below the nuclear density, and there are several laboratory experiments which puts a strong constraint in this part. But in this range, it starts becoming very fuzzy. I mean, it's very difficult to do experiment in this part of the density pressure relationship. And remember that this plot in density and pressure is in log scale, so these differences are not as small as you may think, because this is a huge dynamic range in density and pressure. However, if you take this one particular equation of state and try to ask that if this is the correct equation of state of a neutron star, then how the mass as a function of radius may look like. And it maps a unique curve in mass radius plane. If you solve a Tolman-Oppenheimer-Volkov equation, which is a fully general relativistic hydrostatic equilibrium equation without any spin. And if you have a spin, there are certain small corrections, but most of the cases, as I will describe in binary neutron star, the spins are believed to be quite small, so this actually is a very good proxy. So here you can see that the differences in radius are quite substantial. And if you can find a mass versus radius curve here, you can always map it back to the density pressure relationship, which again gives you a very good understanding of the microphysics of the internal matter in the core of the neutron star, which is of very prime interest. Now, let me come to the constraint that we presently have from observational side. So, again in this diagram, there are several equations of state. Mostly the nucleonic equations of state are plotted in blue curve. Nucleons plus some amount of exotic matter, some amount of hyperon are plotted in this pink or magenta type color, and pure bare quark matter are plotted with strange quark matter curve, this SQM1 and SQM3. So a few tens of years earlier, we had a very good estimate of neutron star mass, where it constrained this neutron star mass estimate was around 1.45 m-sun. So what it means is that if there is a neutron star equation of state which cannot produce as massive a star as this observed one, then this is a ruled out case. So in this particular case, it doesn't put a very strong bound, but subsequently you start discovering more and more massive neutron star, and very recently in 2010 actually you discovered a neutron star which is almost as massive as 2 solar masses, to be precise 1.97 plus minus 0.04 m-sun. That's by demo raised using Shapiro delay. and immediately you see a bunch of equation of state fails to produce as massive neutron star as possible, as observed. So immediately those neutron star equation states are ruled out. However, this has limitation. Limitation in the sense that you can still see a bunch of equation of state can produce much more massive neutron star than 2 solar mass. And you cannot expect to discover more and more massive neutron star, because if your correct equation of state is say SQM3 or AP4, you won't see a more massive neutron star than this allowed region, but there will be a bunch of other equation of state which can equally produce as massive one. So the take-home message is that it will be only possible to get a single out equation of state only if the most massive equation of state is the correct one. Otherwise, all the equation state which produce higher and higher mass will be valid always. So you need something more. However, if you can, from this diagram, you can see not only mass but radius also is a physical quantity which gives you a very good handle on your equations of state. But unfortunately, radio observation cannot put a constraint on the radius. It can give a very good constraint on the mass, but not radius. So we need something extra. Here comes the X-ray observation. In principle, X-ray observation has a promise that it can simultaneously measure the mass and the radius from a same astrophysical neutron star, and can thus produce a strong constraint on the mass radius parameter plane. So these figures are taken by some amount of, to certain extent, a recent work from Ozel, Groover, and Gouliard, some 3 different group of people to see that what kind of bound a mass radius plane you can get from several neutron star observation. However, it seems that this particular method is extremely sensitive to the neutron star atmosphere model. So let me describe how actually one can estimate the mass and radius of a neutron star from X-ray observation. The method they use is called thermonuclear X-ray burst. What happens is that these neutron stars are have a companion which is a low mass X-ray binary type. And this low mass X-ray binary fills its Rousseau and donates mass to the neutron star in the which is companion and going around to this low mass star. It produces an accretion disk, matter accretes on the neutron star surface, it keeps on accumulating, the accreted matter are mostly hydrogen, and it keeps on accumulating after a certain amount of time, typically a few weeks to a month, depending on mass accretion rate. The column of the accumulated hydrogen gives enough pressure and temperature at typically a few tens of meters in the from the surface layer to the interior of the star, which satisfies a thermonuclear ignition condition. So this hydrogen goes through either triple alpha reaction or proton capture and becomes essentially a locally thermonuclear chain process, which burns the entire surface of the star, which temporarily covered with hydrogen. So you see an immediate flash in X-rays. You get a huge flux, and in certain cases, you see the flux is so high, it reaches the Eddington luminosity. Once it reaches the Eddington luminosity, you can estimate the mass very well. And if you take the spectra from this thermonuclear X-ray burst and try to do certain modeling to eliminate other effect from the accretion disk and neutron star atmosphere, what you are left with is a purely single temperature thermal spectrum which has temperature and area. When you do this fitting of the spectrum from this X-ray observation of thermonuclear X-ray burst. So this area gives you a surface area of the neutron star from which you try to estimate the radius. So in principle, this is a very nice and novel method. However, if you have an atmosphere which is mostly unknown composition, then what happens is that the thermonuclear X-ray burst actually, if the radiation that it emits goes through lots of scattering in the atmosphere, and it contaminates the actual physical radius of the star. that creates a lot of problem. So then there is another method from X-ray astronomy where people look at the quiescent emission where you do not have accretion disk and you try to model almost a single bare neutron star. But again, people have faced a lot of problem with modeling this neutron star atmosphere, although it doesn't have subsequent component, but the atmosphere itself seems to be sufficiently large so that you get a large error in the mass radius plane, and this method also seems to be very limited in its scope. So I will probably skip this slide and I will come back if the time permits. It's a bit complicated. So let me go directly to the neutron star in the gravitational wave era. The advent of ground-based second generation detector, like advanced LIGO, advanced Virgo and Kagra, and also LIGO India now approved, has opened up a new era of gravitational wave astronomy, as we have heard from a number of speakers earlier. And here the neutron star, here the advanced LIGO horizon as a function of time as projected in the future are shown, and you can see that for a binary neutron star, the reach of the advanced LIGO detector can be as high as around 200 megaparsec, and here we expect to have several binary neutron star detection, and it can be very useful to have gravitational wave data from binary neutron star to possibly look for any signature of equation of state. Now, let me come to the tidal deformability in this context. During the inspiral phase, actually the very late inspiral phase, the gravitational field of one component neutron star deforms the shape of the another neutron star due to tidal interaction, and this can be expressed in this particular form, where this is the quadrupole moment to the external field, which is denoted by this quantity, and the lambda is called tidal deformability parameter, which is essentially proportional in this linear region. Now, if we see how its effect can come in the gravitational waveform signature, we can see that for a black hole-like object, the gravitational waveform will look like these black dots, whereas if you put some matter, some physical object, you can with different equations of state, like APR, H4, or MS1, where you have an increasingly large radius, you can see at late inspiral stage, the phase of the waveform differs. In this part, you can observe. And let me remind you that a unique equation of state maps to a unique tidal deformability, and the effect is very sensitive to the radius of the neutron star. Here I have plotted r to the power 5 part, assuming the K2 is not changing, which is approximately correct to get the order of magnitude estimate from this realistic equations of state. So you see, this is a log scale, and their differences are really, really large. Like radius, if it is roughly double, then you get a tidal deformability, which is roughly 30 times as much. So this is a very sensitive to the radius of the neutron stars, this quantity, this tidal deformability. So if you can estimate that, you can get a very good handle on the neutron star radius. Now, estimating lambda from gravitational wave observation is a very interesting thing, and people have done it for past few years, and people have seen that unfortunately, from a single gravitational wave event, you cannot expect strong dependence on strong constant in the tidal deformability parameter in the advanced LIGO design sensitivity. You can only distinguish them where the equations of state are really, really steep. However, if you have an Einstein telescope and working in its design sensitivity, then you can very easily disintegrate, disentangle all these equations of state depending on their tidal deformability parameter. However, here it will be interesting to mention that if advanced LIGO comes with another upgradation, then in 2.5 generation, as Rana might say, then I guess the sensitivity curve will limit us to see beyond this line perhaps, which will be very useful to disentangle this tidal deformability. This has also triggered certain large-scale simulation primarily from Nikkei group, where people have combined a large number of binary neutron star objects and a very sophisticated and highly fully Bayesian parameter estimation way of estimating tidal deformability from a number of neutron stars. And you can see that if you have a detection of around 25 or 30 binary neutron star objects, and if you combine the effects from each individual one and put a joint constant on the tidal deformability parameter, you can start distinguishing between very hard, intermediate, and soft equations of state. However, there seems to be a few potential problems, such as the bias, such as the uncertainty in the component mass distribution, putting a bias in the tidal deformability parameter, as well as spin issue, which can potentially limit in this parameter, tidal deformability parameter. In this context, I would very briefly like to mention that we are also pursuing some kind of study in this fully Bayesian parameter estimation, and you can see that from an individual BNS event, you cannot get a good constraint on the neutron star equation of state. In this particular case, we essentially use the same simulation that Nikkei group used. The injected waveform is Taylor F2 and also recovered with Taylor F2. And in this particular case, it shows that a single event is not perhaps strong enough, thus reconfirming it. Again, we started combining multiple events, and we see as we go around 30 BNS events, the total constraint, the joint constraint on this tidal deformability parameter start becoming stronger and stronger. In this y-axis, I am showing the logarithm of the odds ratio between two equations of state, EoS-N and EoS-AU. And if you go back quickly to this plot, this is EoS-AU and EoS-N is this curve, then beyond 25 to 30 events, you can see a very strong statistical way of distinguishing them. Now, there is another small issue. Actually, it's not quite small. The issue is that we have certain systematics in the waveform itself. And this analysis was demonstrated by Leslie Wade, Ben Lackey, and Jolian. What they did is that they simulated a neutron star waveform by doing a Taylor F2 injection and tried to recover with various different I think they actually injected various different waveforms and always recovered with Taylor F2 waveform. And they found that there are systematic biases in tidal deformability parameter when they use different families of waveform. And this is a potential problem. However, in recent time, there are efforts going on from Barnouzi's group and also Hindra group with AEI, Alessandro Bonanno, and along with Hoto Keizaka from Japanese group, where they are creating a very reliable, effective one-body model, which has been attached with several tidal effects, mostly very recently the dynamical tides effects, and calibrated with numerical relativity waveform, and they agree quite well. So in these particular cases, they stitch the analytical waveform for first 5 cycles, and then they evolve them, and you see a very good agreement till very late in spiral stage. That gives us a good promise. However, we need to remember that those waveforms are extremely slow, and we need to speed up by using some empirical, perhaps a reduced order model. And now let me come to the last topic, where I will briefly discuss about the NR simulation of post-merger, where essentially you have 2 neutron stars inspiring towards each other, and in this axis you can see the density of the 2 neutron stars. And let me play the movie. Here. So you see the 2 neutron stars coming towards each other and then touching and merging. Here in this arrow you can see the velocity field, and in this axis you see the density profile, and here you see the curvature of the space-time. So what happens is that when these 2 neutron stars merge, at certain stage you can see that there are some bar-like structure. It's not completely axisymmetric. So there is some kind of bar-like structure, and when it keeps on spinning, it produces a characteristic gravitational waveform, which is a function of radius. Let me come to the next slide, where we can see if you generate this kind of binary neutron star merger, depending on its equation of state, which gives a certain radius, you get different characteristic length, and that defines different characteristic frequency in the emitted gravitational waveform. So if you can observe some of this, any of this particular characteristic peak frequency in gravitational wave band, then in principle you can constrain this neutron star equation of state. In this particular case, this is, I think, advanced LIGO design sensitivity, and this is the advanced LIGO initial sensitivity, and this figure is taken from Masaru Shibata group. There I stop. I thank the organizer for the invitation of the talk. Many thanks to the audience, and I will also like to thank several of my collaborators, and finally my DST project. And let me summarize this talk. I briefly mentioned about the importance of neutron star equation of state as a fundamental physics, and discussed the constraint coming recently from radio observation, that coming from the X-ray observation, elaborated the estimation from tidal deformability in gravitational wave signals, mentioned the possibility of constraining neutron star equation state from the post-merger phase. However, I couldn't sort of cover in this limited time the possible way of constraining neutron star equation state from NS-BH system, where you can have a tidal disruption which will essentially depend on the particular equation of state. And by measuring the mass and spin of the black hole, you can, in some cases, distinguish which type of equation of state the neutron star is possibly made of, and a few other possibilities I completely missed. Thank you.
Questions for Arunava? Yes, Rinas. That means if the equation of state is softer, it will show a bigger effect in the gravity wave signal, right?
If you say about the post-merger, then it is.
See, if the equation of state is softer, then your distortion should be larger.
Smaller.
Smaller.
Right?
Yeah. So
Object is more particle. So it's stretchable, right?
yeah, but you have a small radius neutron star, then it's more like a point object. The tidal field is proportional to the diameter of the neutron star, right?
No. If you consider point particle, then there is no tidal distortion.
Exactly.
So take a finite size neutron star.
Yes.
Then stiffer the equation of state.
No, not that way. The stiffer equation of state will give a bigger neutron star for the same mass. That means the tidal field that it feels at two extreme ends are larger.
And how hot does the neutron star get in the pre-merger state?
How hot? Yeah. Pre-merger means before touching, it's really cold. It's essentially zero temperature fluid is a very good approximation. But once they merge, then they become very hot. And that is, you need some finite temperature correction to this equation of state, and which some of the nuclear simulations can provide.
Any other questions? Go ahead. So, Chishman, can you read out that question from TeamSpeak? Maybe to save time, he can write it in the chat box. In the meantime, any other questions from the audience here? I'll ask a quick question, maybe somewhat of a non-mainstream question. How do you rule these out as maybe boson stars, obeying some other equation of state?
Okay. So if you have a specific equation of state, then you can perform the same exercise. But if you do not have a specific equations of state, then you don't know. In principle, they are possible. They are boson star.
But X-ray observations alone have put constraints, right, on certain types of boson stars.
Okay. That for a specific case for this CSW equation of state, we could show that if you combine the radio observation and the X-ray observation together, then there is no allowed parameter space for one particular type of boson star equation of state family, that is proposed by Kolpi, Shapiro, and Wasserman there. So in that particular family, it's true that we have ruled out, but if there is a different type of interaction which leads to a different composition of boson star, then we can't yet. If there is a specific equation of state, one can test this exercise similar way and say whether it gives some constant or not.
Archishman, do we have that question on team? Okay.
Okay, so this is a very good and relevant question. So now let me answer it with the caution, word of caution that is quite uncertain regarding the predicting the exact light curve of the binary neutron star merger starting from a particular neutron star equation of state. This is because mostly this amount of ejecta, computing the amount of ejecta is very sensitive to the numerical, particular type of numerical simulation you are doing. And it can have, for a given equation of state, depending on whatever post-merger physics you are putting in, like whether you consider certain neutrino cooling and winds from the neutrino that drives this certain amount of mass can produce a different amount of ejecta. Having said that, even if you know the amount of ejecta, you need to know a specific composition of it so that it goes through subsequent nuclear reactions like R process or S process nuclear synthesis, which will eventually create a lot of radioactive element, and then they will decay to more stable elements. So these are all very uncertain. However, if it happens in of the order of 100 megaparsec distance, then it can possibly be seen by several electromagnetic follow-up telescopes, mostly optical and IR, I guess. That's what the literature says. Now, I know that this is a vague question, but sorry, this is a vague answer, but I don't have a better answer. But let me know if you have anything specific to ask.